Hi and welcome back to this OpenGL tutorial. In this tutorial we want to understand the camera in OpenGL world. In particular we want to compute the mathematical expression of the view transformation matrix. So we want to see the scene from the camera. When we're talking about the camera view space, we are talking about all the vertex coordinates as seen from the camera's perspective as the origin of the scene. The view matrix transforms all the world coordinates into view coordinates that are relative to the camera's position and direction. So this means that these coordinates are expressed respect to a frame attached to the camera itself. How we can see the camera? So we are in the following situation. It's important to understand that when we place a camera in the world with a specific position and orientation, the camera is looking in the negative direction of its own zeta axis. With this in mind, we are ready to compute the mathematical expression of the view transformation matrix. So, in this image we have the world frame and the camera frame. We have a general point in the scene. This point is vertex. We have the OP vector, and the OP vector is the vector position that identifies the point P respect to the world frame. We have the OCP vector as the vector position that identifies the point P respect to the camera frame. And finally, we have the OOC vector that identifies the origin of the camera frame respect to the world frame. These vectors are related through this mathematical expression. Okay. We need to express the OCP vector respect to the world frame, and we know that we can compute this operation using the rotation matrix that describes the orientation of the camera frame respect to the world frame. So we can express the OP vector as the sum of the OC vector and the OCP vector expressed using the rotation matrix respect to the world frame. Now, if we multiply both members of the first relation using the rotation matrix that express the orientation of the camera frame respect to the world frame, we have this second mathematical relation. Now, from this second mathematical relation, we can isolate the OCP vector, obtaining the third mathematical relation. Now, if we introduce the coordinates of the point P respect to the world frame and respect to the camera frame, and if we introduce for this point the homogeneous representation, we can express the third mathematical relation in this form. And this mathematical expression allows us to transform a point expressed in homogeneous form respect to the world in point expressed in homogeneous form respect to the camera frame. And the matrix that allows us to perform this transformation is the view transformation matrix. We want to call this matrix as the inverse of the T matrix. and the T matrix is the homogeneous transformation matrix that express the position and orientation of the camera frame respect to the world frame. Now we are ready to define in C++ code in our OpenGL program this matrix. Okay, let's see the camera class. And let's start with the H file. In the H file, we define the interface of our camera class. The camera class allows us to represent the camera in our OpenGL world. We have the method setPosition. In order to define the position of the camera with respect to the world, we have the method setOrientation in order to define the orientation of the camera with respect to the world, and we have the getDirection method. The getDirection method allows us to get the direction where the camera is looking. And finally, we have the viewTransform method. This method executes the view transformation. In order to represent position and orientation, we define some variables in the private section. And we have the transformation matrix represented in array form. Now let's see the implementation of the camera class. The set position and orientation are very easy. Now let's see the view transform method. And in this method, let's start with the homogeneous transformation that describes position and orientation of the camera frame respect to the world frame. We have the rotation matrix representation in the first column, second column, and third column. And the fourth column is the position representation of the camera in the world. At this point, we need to realize the inverse of this homogeneous transformation. We know that the inverse of this homogeneous transformation matrix is the view transformation matrix. The view transformation matrix that allows us to express point in the world frame in point expressed respect to the frame attached to the camera. Okay, first we compute the last column of the inverse homogeneous transformation. We need to remember the representation of the view transformation matrix we have seen in the last slide. Now we can define the complete inverse homogeneous transformation, position orientation, of the world frame respect to the camera frame. This matrix is the transformation matrix. It's not difficult, to identify in this matrix the matrix we have seen in the last slide. We have the first column, the second column, and the third column, and the fourth column. Now we are ready to build the homogeneous transformation matrix in array form using these two expressions in our code. The getDirection method is very interesting. We want to see in this method the implementation that allows us to get the direction. The direction of where our matrix is looking in the world. We compute the negative zeta vector with zeta, the versor of the frame attached to the camera expressed in the world frame. we are using the rotation matrix in order to perform this transformation, as we have seen in the mathematical expression in the last slide. Now, let's see the main method. In the main method, we have the method init scene. In this method, we build our camera object. In this method, we have also other methods. The method that allow us to load textures, the method that allow us to build the ground and roof, and the method that allow us to build the walls. We will see the implementation of these methods and other methods in the next tutorials. Now, after the camera object definition, we see the draw methods, because in the draw methods we will use the camera object. First, we want to place the camera in the world, so we set the position, the orientation, and we execute the view transformation. We get the camera direction, and we introduce in the OpenGL world the ground, the roof, and the walls for our scene. We update the delta time, and we need to swap the buffers. Now we are ready to see in action the view transformation using our camera class. Start without debugging. Okay. We can rotate the camera using left and right keys, and we can use other keys in order to move the camera in the world in different directions. Okay, that's all for this tutorial. See you soon in the next tutorial, and thanks for watching.